Solve each equation by first rewriting the expression in each part with the same base. You can refer back to problem 3, 132 if you need a reminder. If we take a look at the first problem, we have two different bases. We've got 8 and we've got 2 are our bases. But it turns out there's a relationship between those numbers. In fact, I'm going to jot down some of the different powers of 2. I could have 2 to the first power is 2, 2 to the second power is 4, and 2 to the third power is 8. So this is the information that I'm going to use here, right? 8 is the same thing as 2 to the third power. So I can rewrite this equation. So instead of placing 8 to the x, I'm going to write 2 to the third. And remember, that is 8, and then raise that to the x power. On the other side, we've got that that's equal to 2 to the 6th power. Now, if I simplify the left-hand side, I've got a power raised to a power, so this is equivalent to 2 to the 3x power. And that's 2 to the 6th. So again, what we discussed in class, you can sit and play with this on a calculator and look at numbers all you want, but it turns out the only time that these two, the left and the right-hand side, are going to be the same, the only time that this is going to be a true statement is if the exponents are exactly the same. 3x has to equal 6 in order to make 2 to the 3x equal 2 to the 6th power. So I'm not going to transform this equation again. What I'm going to do is I'm going to say, look, I want this exponent, 3x, to be the same as this exponent. So it's not that I'm ignoring the 2's. I had to get the 2's there first. But because they both have the same base, I can now focus on making the exponents the same. And if I make the exponents the same, they're the same. So it's a pretty straightforward equation, right? At this point, I divide both sides by 3, and I get that x has to be the number 2. So when x is 2, this is true. And you can plug that back into the original equation. It turns out 8 squared is the number 64. And 2 to the 6th power, that's 2 times 2, 4, 8, 16, 32, 64. So when I have 2 to the 6th power, that's also 64. So because the left and the right-hand side are the same at this point, right, 2 is exactly the value that makes this true. Let's look at another example. Or it's actually not an example, it's another problem. For this problem, let me clear all the writing here. Again, I have different bases. I've got 9 that's being squared, and I've got 3 to the 2x plus 1. Well, again, the smaller of the two bases is the 3, and I don't know that I'll always pick the smaller of the two, but I might. But if I think about this, 3 to the first power is 3, 3 to the second power is 9, 3 to the third power is 27, 3 to the fourth power is 81. So I don't need to look any further than this, but there's more. In fact, I could go the other way. 3 to the 0 power is 1. 3 to the negative 1 power is 1/3. But I think the one that we need to focus on is 3 squared is the number 9. And the reason why I like that one is because I'm going to convert it so that my bases are both number 3's. So I'm going to rewrite the left-hand side. Instead of having 9 squared, I'm going to write 3 squared, that's the number 9, and then square that. Over on the other side, I have 3 raised to the 2x plus 1 power. Well, if I look at that, 3 squared and then squaring that, that's equivalent to 3 to the 4th power. And it's worth it to look at this. I'm actually multiplying 2 times 2 to get the 4. I have 2 of these, right? I have a 3 squared times another 3 squared. And each one of these produces 2 factors of 3 rather. So this is 3 times 3 times 3 times 3. So it's 3 to the 4th power. Over on the other hand, on the other side, we've got that this is 3 rather to the 2x plus 1 power. Now, if I look closely at this, right, at this point, because I have identical bases, they're both the base is 3, I can focus now on what I have to do to make the exponents the same. The bases are already 3, and if we can force the exponents to be the same number, that would find a solution to this equation. So that's why I'm not really transforming this equation, but I'm looking inside at the bases, and I'm saying, hey, look, I want 4 to be the same thing as 2x plus 1. So I guess I'm looking at the exponent on the right-hand side. I'm saying that I want that 2x plus 1 to be the number 4. I take away 1 from both sides, I get that 3 is 2x, and then I divide both sides by 2, and I get 3/2 is what x is. So when x is 3/2 or 1.5, this equation up above is true. And you could plug that back in to check it. If I plug 3/2 in there, take a look at it. I've got 2 times 3/2 and then plus 1. Well, when you multiply 2 times 3/2, you get 3, and 3 plus 1 is 4, so this is 4. And if you consider on the one side, I've got 9 squared, which is 9 times 9, which is the number 81. And on the other side, I've got 3 to the 4th power, which is 3 times 3 times 3 times 3. Well, 3 times 3 is 9, times 3 is 27, times another 3 is 81. So probably overkill, but definitely x is the number 3/2. 3/2 is the value that makes that true. And I believe there's one more problem here. Let's clear the ink. The last one has a base of 4 and a base of 1/2. And let's see what to do. I'm gonna take a look at some powers of 2, and in fact I'm gonna expand this list a bit. I'm gonna have 2 to the 0 power, and I know that that's equal to 1. 2 to the 1st power is 2. 2 to the 2nd power is 4. 2 to the 3rd is 8. 2 to the 4th is 16, etc. But if I go the other way, 2 to the negative 1 power is 1/2. And it might be, you might be like, really? That's what that is? You could consult your calculator and evaluate 2 to the negative 1 power, and it'll say 0.5. But also, if you just consider this, right, 2 to the negative 1 power, if I want to deal with that negative exponent, I can multiply that by 2 to the 1st power over 2 to the 1st power. I know in my numerator, I end up getting 2 to the 0 power, which is the number 1. And in my denominator, I just have plain old 2. So you can see it is indeed 1/2. But now that that's patterns there, I might try and focus on that, right? 2 to the negative 1 is 1/2. 2 to the negative 2 is going to be 1 over 2 squared, or 1/4. 2 to the negative 3rd power is 1/8. Now, the values that we want to focus on are right here. Actually, we could focus on a lot of things. We could change more than one thing. But let's look at this one. And actually, let's look at the 4 also, right? So I'm going to switch this so that my base is the number 2. So I'm going to first of all begin by replacing this 4 with something that's equivalent to it, namely 2 squared, right? 4 is the same as 2 squared. So I'm going to rewrite this as 2 squared in parentheses. Again, that's the number 4, and I'm going to raise that to the 2x power. On the other side, if you look closely, the 1/2, right? 1/2 is the same thing as 2 to the negative 1 power. So I can rewrite this 1/2 as 2 to the negative 1 power and raise that to the x plus 5 power. Well, same thing, right? I'm going to raise a power to a power on both the left and the right hand side. Over on the left hand side, I get 2 to the 4x. 2 to the 4x power. I'm multiplying this 2 times this 2x. I'm getting 2 to the 4x. And on the other side, I'm going to multiply both of those by a negative 1. So my base is 2, but when I multiply by negative 1, I'm going to get a negative x and then a negative 5. So at this point, I have the my main goal is to get the same bases. So now that I have the same bases, we can ask ourselves, well, what does it take to make 4x be the same thing as negative 5x plus 5? So I'll come over to the right here and just, I'm going to ask myself, hey, I want these two to be the same. What's the value of x that would make them the same? If I add x to each side, I have 5x equals negative 5. And then I can divide both sides by 5, and I get that x is negative 1. So it turns out if I plug negative 1 into the original equation, I'm going to get the same thing on both the left-hand side and the right-hand side. This is a problem we haven't looked at for a while. It, I think, involves dimensional analysis, and that's the approach I'm going to take with it. And there's a couple, giant ones that we have that we can use to multiply things by. And the first sentence is actually one of them. It says, every ton of recycled office paper saves about 17 trees. So one of them I could say is 1 ton of recycled paper saves 17 trees. And if you think about it, those are equal quantities, right? A ton of saved paper equals a recycled paper saves 17 trees. So that's a giant one, and I can multiply by 1. A textbook publisher recycles 8,000 pounds of paper. Okay, so we've got an input there. They're saving 8,000 pounds of paper. And they also give us a hint. They said that 2,000 pounds is equivalent to 1 ton. So let me write that. 2,000 pounds is equivalent to 1 ton. Now the question that they ask is, how many trees did it save? So if they're saving 8,000, if they're recycling 8,000 pounds, right? Our goal is to figure out, hey, 8,000 pounds is equivalent to how many saved trees? Well, let's start with our input, right? Our input is 8,000. And that's pounds of paper. And I'm going to take that number and I'm going to multiply it by, I want the pounds to cancel out. So I'm going to multiply that by this giant one, the fact that 1 ton of recycled paper is 2,000 pounds. Now, the reason why I've done it this way is, if you'll notice, on the one hand, I've got pounds in this numerator, right, 8,000 pounds, and I've got pounds in this denominator. Well, those units are going to form a giant one in and of themselves. So right now, I've gone from 8,000 pounds to 8,000 divided by 2,000 tons. So the answer to this problem that you see on the screen is now no longer pounds times tons divided by pounds. That answer is tons. We're looking at tons. And what we want to do is we want to multiply this by something in order to convert it into trees. And this giant one that I have sitting right here is helpful, except I need the reciprocal of that relationship because I want tons to be on my denominator. I want to cancel out tons with the tons that I currently have. So I'm going to do one more multiplication problem. I'm going to multiply it by this giant one. 17 trees is equivalent to 1 ton of saved paper. So again, you can see here I've got a ton in this numerator and a ton down here in this denominator. So of all the units that I have left over, the only unit that's left is trees, right? So this forms a giant one, right? A ton over a ton is a 1, and these form a giant 1. So my answer looks like this. It looks like 8,000 times the number 17 divided by 2,000, and these are trees. So I can see the dimensional analysis has essentially told me what operations I need to perform to figure out how many trees are equivalent, saved trees are equivalent to 8,000 pounds of paper. And I know intuitively there's ways that we can probably work our way through this, But I encourage you to think about dimensional analysis because a lot of times these can string along and become much, much larger. And sometimes we're not really necessarily familiar with the unit. So this technique always works, and it's something that your chemistry and bio teachers are going to be really super happy that you're able to do. By the way, I still haven't answered the question, but I'm not really concerned with that. It turns out 8,000 divided by 2,000 is the number 4. So I've got just 4 times 17 trees, and in order to get that answer, 4 times 17 is 68. So yes, it's important that I do finally get down to 68 trees, but I think more important is the path that we go through to get our starting input 8,000 pounds and multiply it by giant 1 so that units cancel out and I am left with just plain old trees. On graph paper, draw a triangle with vertices at -3, 3, 4, 3, and 2, -2. Do it. Go ahead. You don't need me to do this. You can do it. Graph them. All right, I'll do it anyways. So at -3, 3 is one of the points. That's point A. Oh, actually, they don't give me the names of these vertices. It's the first one. Then I've got over 4 and up 3 as well. That's nice. It's a horizontal line. And then finally, I've got over 2 and down 2 units. So this is my final vertex. Now, when I look at this, they're asking me to find the area of this triangle. And area, area is product of base and height, but there's other ways you can deal with finding the area of this particular triangle. And I can go through all kinds of dissections and ways of looking at this, and I don't know that that's helpful or not. I could point this out. I could take this and create 2 different rectangles. Probably it would be helpful if this was a light color. So let me do this and this color and this color. So if you look at this rectangle that I've just drawn, half of it contains my triangle, part of my triangle, and half of it does not. And I can also draw this rectangle. Half of that contains my triangle. Half of that's in my triangle and half of it's not. So if I could find the area of those things and then be real strategic about not including all of them, but just the half, right? Because half of the orange one is in my triangle and half of the green rectangles in my triangle, that would give me the area of the triangle that I'm looking for. Well, this yellowy one is dimensions 2 by 1, 2, 3, 4, 5, 2 by 5. So it's 2 by 5 or it's 10. And the other one, the green one, has a dimension of 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. So it's 5 by 5, which is 25. Now, the area of the rectangle is not exactly the sum of those two, right? The sum of those is 35. And I say it's not exactly that because it's half of that. So the area of our triangle is 35 divided by the number 2. And I could look at that a couple ways, right? Part of the area is this 5, and part of that area is half of 25, which is 12.5. So when I combine those, I do get 17.5. And yeah, 35 divided by 2 is indeed 17.5. Another way you might want to look at that is if you consider this the base of this triangle, right? And this line, the height of the triangle, we can multiply the base times height. And but if you think about that, what we're finding is the area of that entire rectangle. We're finding the 35. And then we're going to take half of that again. So in this case, the base of this is 1, 2, 3, 4, 5, 6, 7. And I'm going to multiply 7 by 1, 2, 3, 4, 5. Well, yeah, if I go about it that way, I've got 7 times 5, which is 35. But then I take half of that, right? 35 divided by 2 is again 17.5. So, all right, overkill. Let's see. Finally, it says translate the triangle 3 units to the left and 2 units up. what are the new coordinates? So I'm going to use just a nice basic black. So every single unit is going to go to the left 3 units. So 1, 2, 3, and then up 2. So that is one of my new coordinates. To the left 3 units and up 2. So 1, 2, 3, and then up 2. That's a new coordinate there, right? These are getting moved. And then this one's to the left 3, 1, 2, 3, and then up 1, 2. This one goes here. So if you look at each of these points, right, this is going this direction, this is going here, and then this point is going there. So my new triangle is this one. And the question asks, what are the new coordinates of the vertices? You know, another way that you can write that is if I consider this xy to be the coordinates of my original triangle, the new ones are going to be at whatever x was minus 3. That's how I move 3 to the left. And whatever y is plus 2, that's how I move 2 up. So if I look at that rule, I could quickly just come up here and I could write down these coordinates, right? 3 minus 3 is negative 6, comma 5. That's one of the points. The other one, 4 minus 3 is 1, comma 5. And then finally, I've got 2 minus 3, which is, 2 minus 3, which is negative 1. And then negative 2 plus 2 is going to be 0. And you can see that those are exactly the coordinates we have, right? This coordinate is at 6, negative 5. I'm sorry, it's at negative 6, positive 5. This one's at positive 1, positive 5, and then this one's at negative 1, 0. Examine the diagram below, it's not at right. Then use the information provided in the diagram to find the measures of angles A, B, C, and D. You can see them in the diagram. For each angle, name the relationship that helped justify your conclusion. For example, did you use vertical angles? If not, what type of angles did you use? So as I look at this, I guess there's some vocabulary associated with these angles. Vertical angles is one of them. Another pair of angles I might consider, I think our textbook might call them a linear pair. So if I look at this angle right here, this angle at C, and the angle right next to it that's marked at 128 degrees, those angles are forming a straight line. And when we have a pair of angles that form a straight line like that, right, it's equivalent to a 180 degree rotation, right, like from this point onto the other. So I know that those two angles have to add up to 180 degrees, rather. I might have said 128. So I know that angle C plus angle that measures 128, right, the measure of angle C plus the 128 degrees has to be 180 degrees. So that means that the measure of angle C will equal 180, and these are degrees, minus 128 degrees. So it's just a simple subtraction problem. So I know that the measure of angle C is 52 degrees. That's one of my angles. Another thing I guess I know is I'm shown that a pair of these sides are parallel to each other, right? This line, rather, not sides, this line is shown to be parallel to this line. And the way that our most textbooks and our textbooks show that is they put these extra kind of arrow things on it. So they're parallel to each other. And when I have pairs of parallel angles, there are certain angles that are in the same location. They're called corresponding angles. So if I look at this angle that's marked 72 corresponds with this angle, right? That because they're corresponding angles, they're both equal to 72. Now this isn't always the case that they're going to be equal to each other, but when the lines are parallel to each other, and they're cut by a transversal like this, and I'll mark this transversal in purple. When they're cut by a transversal and they're parallel lines, it forces these corresponding angles, the ones in the same location, to be congruent. So that's going to allow me to make a couple of observations. So since this is 72, I definitely know that angle B and the 72-degree angle are going to be a linear pair also. So just like before in the previous example, I could say that the measure of angle B plus the 72-degree angle equals 180. They have to add up to a straight line. So the measure of angle, and I should use a lowercase b, sorry, is equal to 180 degrees minus 72 degrees. And by subtraction, that gives me that the measure of angle B would be 108. Well, now, and that's true because why? Well, I haven't put my reasons down for anything yet. This is true because of it's a linear pair. In fact, both of these I would say linear pairs. That happened twice. This linear pair, though, needed something else. I also needed the corresponding angles. And the corresponding angles that gave me the 72 down below. Now the next one I think is just easy, right? Measure angle A and B have to be congruent to each other because they're vertical angles. Basically, anytime that we have a pair of lines that intersect, the angles that are across from each other, for example, this pair that I've marked in black and this pair that I'll mark in this yellow color, those are vertical angles and they're always going to be the same size. They have the same number of degrees. So I know that the measure of angle A also is 108. And the reason why I can assert that so quickly is because it's a vertical angle with angle B. So they both have to be the same. And then I guess, I don't know that you know this definition. I think it's something that's introduced perhaps in 8th grade, but there's one other pair of angles that I see here. And they are the ones that are labeled D and C. And those also have a name, right? This angle D and this angle C, some people refer to as alternate interior angles, or they're opposite side interior angles. So why do we call them that? Well, if you consider our parallel lines, everything in here is considered the interior in between the two lines. And in terms of our transversal, they're on alternate sides or opposite sides of the transversal. So you could also call them opposite side interior angles. By that I mean they're on opposite sides of this transversal. Again, the transversal is the one that I marked in orange. That's what I'm speaking about. This is our transversal. It's traversing the two parallel lines. So we could write down that angle, the measure of angle D would also have to be 52 degrees. And the reason for that is it's an alternate interior angle. Yeah, that's it. So I obviously have an unfair advantage in that I don't need to copy the original shapes. However, when you're doing that, please consider looking at just the kind of the internal pattern. So if I'm looking at this shape A and I start at this point, it doesn't matter exactly where that starting point is, but the next point has this pattern of up 1 and then over 1, 2, 3, 4. So this is where the next one is, right? So if this is the first point, this could be the next. And then on my graph paper and my composition notebook, from there I would go down 1, 2, 3, 4, 5, 6, 7, and then back 1 from there. So that allows me to get exactly the same triangle. Now, if I'm reflecting an A, it says reflect figure A across line L. That's going to look like this, right? This has to be equidistant on both sides, right? So that's going to be where this point goes, right? This point that was in green is going to land at this point. The next one I could basically use this internal pattern, but kind of backwards. I can go over 1, 2, 3, 4, and then down 1 from there. So if you look at it, I see the exact same up 1 over 1, 2, 3, 4, except backwards, up 1 and then back 1, 2, 3, 4. So this is going to be part of, and that's terrible how it's curved. That's going to be part of it. And the other one is probably just simple if I just go across 3, right? 1, 2, 3. So my last two segments would be like this segment and this segment. Now, if you want these to look even better and more convincing, use a ruler, but definitely make sure those points are located in the correct spots. If I rotate figure B 90 degrees clockwise, let's see, clockwise about point P, that's kind of nice because it's if I'm starting here, right, point P is going to land at the same spot. And this point up here is going to be pretty easy to see where it goes because I'm going 90 degrees. It's just up 1, 2, 3, 4, 5. So I'm going to go over 1, 2, 3, 4. So this is where this is going to go. And then if that point is there, right, see from there I go up 1, 2, 3. So I'm going to just go up 1, 2, 3. That's my next point. And then I need to go over 3, so 1, 2, 3 right here. And then finally, there's a little bump out, and then it just returns back to itself in 2, yeah, like this. So there we go. So if I rotate this 90 degrees clockwise about the origin, yeah, like the clock moves, this is where I would go. So let's try part C. I'll mark the vertices that I have with these green dots. And one of the things I know is that, you know, if I've got a line of reflection, right, the distance from a point to the line of reflection measured along perpendiculars will be equal either way. So I know that this point is going to go exactly there. And I could do that again for this point. There's like, there's 1, 2 there, so I go 1, 2 there. That gives me another point. Let me try that again. So I've got 1 and just a half of 1, a half of 1, and 1. So now this point is going to be here. And this one's got like 1, 2, 1, 2. So we are now at this point. Oh, I was supposed to use red. So I'm kind of getting an idea of what it's looking like, right? I can see the shape. At this point, I think I might just kind of count. There's like 1, 2, 3, 4, 5 here. So I could just go 1, 2, 3, 4, 5. So that's that back side. Geez, and then I go up 2. Then I go on a diagonal for just 1. Then I'm going to come back 3 to connect it back. So there it is. And actually, you know, now that it's there, I can see, yeah, that looks accurate. Let's look at the last one here. It says, rotate this figure 180 degrees about point Q. 180. Well, as we discussed in class on, what was that, Wednesday? If I do a 180 degree rotation, one of the things I observe is that the slope patterns, the two values in it stay the same, except they just both change signs. So what I mean by that, if I consider starting at Q, and I want to talk about this particular point here that I've marked in green, to get there from Q, I would go up 2 and then back 1, right? That's up 2 over 1. Well, to get to where it lands after it rotates through 180 degrees, I'm going to go down 2 and then to the right 1. So this point, and I'll mark it in red, here is corresponding to that point that I've marked in green. So that's kind of like the front of this ship, whatever it is. Now, I don't have to do all of these points like this, but I want to do just one more at least. Let me erase those black lines from. Let me do one more. If I go to, let's say, this point, this is up one, and then to the right one. So corresponding, that would be down one and back one. So you can see they're just the opposites. So this point right here corresponds to the other point that I've got below there. Let me delete those little line segments. And I'll just do this one last time. So to get to this final point, and once I've got this, I think I could easily figure out the rest of it. I'm just going to go up 1, 2, 3, 4, and back 1. So I'm going to go down 1, 2, 3, 4, and back 1. So this point here is exactly where it would land. So again, their slope patterns are, the signs are the opposites. No, yeah, the signs are the opposite. They're still the same direction. It's just that they change signs. I just accidentally deleted a point, and it was here. Let's see, this point was the one that was up 2, back 1, so down 2. This is it. Okay, so now that I've got that, I can see that these are just 1, 2, 3, 4 back. So I can go 1, 2, 3, 4 back and 4 back. So everything is here. And probably a ruler would be much nicer. But there we are. It's our rotation of 180 degrees about point Q. Solve each of the following equations. Explain or justify each of your steps. And be sure to show your work carefully and check your answers. That's a tall order. That's a lot of requirements for this problem. So let's look at the first one in A. The first thing I'm going to do is I'm going to divide both sides by positive 2 rather. And when I do that, I get 3x minus 4 is equal to 11. So what did I do? I used something called the division property of equality, but I divided both sides by a non-zero number. Next, I'm going to add 4 to both sides. So this is an example of the addition property of equality. If you have things that are equal, and you add 4 to each side, you get equal things. So and now I'm going to divide both sides by 3. So this is exactly the same reason I had up above, right? It's division property of equality. I'm dividing both sides again by a non-zero number. So we get that x is 5, and I'm going to plug that into both the left and right hand side and verify that I get the same thing. So over on the left hand side, I've got 2 times the quantity of 3 times 5 minus 4, and I'm seeing if that's the same as 22. 3 times 5 is 15, so I've got 2 times 15 minus 4, which is 2 times 11, which is indeed 22. So you can see that 5 is the value that makes this statement true, right? It makes both the left and the right-hand side equal to each other. So that is the solution to this equation. Our next equation, I'm going to go ahead and, if I look at the left-hand side, right, if you remember when we had our algebra tile expression mats, we had a positive region and a negative region. And when I moved things out of the negative region, the signs had to change. So, and we actually called that the definition of subtraction. To subtract is to add the opposite. So instead of the negative x plus 4, I can write this as a negative x and a minus 4. So both of the things came out of the negative zone and they changed their sign. On the other side, I'm going to use the distributive property, and it'll give me 12x minus the number 30. So actually, in a way I could think of both of them. If I think about this as multiplying by negative 1, I use the distributive property on both sides. I'm going to go ahead and add an x to both sides. That gives me 13x minus 30 equals negative 4. I'm going to add 30 to both sides of this. That gives me that 13x is equal to negative 4 plus 30 would be positive 26. And again, let's see, the last two steps, what I've done is I've added something to each side. So this is just, both of them are addition property of equality. And what we're just saying is if you have equal things and you add the same thing to both sides, you get equal things. And then finally, I'm going to divide both sides by 13. That'll give me that x is the number 2. And that's an example of the division property of equality. Very important to remember when you're using the division and multiplication properties of equality that it has to be non-zero values that you're multiplying by. Okay, so if I was to check this then, right, I've got two sides of this equation. Over on the left-hand side, I have 6 times the quantity of 2 times 2 minus 5, which looks like 6 times 4 minus 5, or 6 times negative 1, which is negative 6 on this side. And over on the other side, I have the opposite of 2 plus 4. 2 plus 4 is 6, so I have the opposite of 6. So in both cases, I've got negative 6. So 2 is the value that makes this absolutely true. When I plug 2 into the equation, both sides become negative 6. For C, we have the equation 2 minus the quantity of y minus 2 and then equals 3y. Over on the left-hand side, I'm going to go ahead and treat this as a times negative 1. So I'll call this the distributive property, but it's going to be 2 minus y minus 2. So that is equal to 3y. So again, distributive property. If I simplify the left-hand side, I've got a 2 and a negative 2. So this ends up just being negative y equals 3y. That's just simplification or addition, right? 2 plus negative 2. The next thing I'm going to do is I'm going to add y to both sides. And I see this error made often. When I add y to the left-hand side, it becomes the number 0. And over on the right-hand side, when I add y to that, it becomes 4y. So this is addition property of equality. And finally, I'm going to divide both sides by 4. Notice I'm dividing by positive 4, which is perfectly fine. On the one side, I've got 0 divided by 4. And when I take 4y and divide that by 4, I have y. So if you look closely, right, 0 divided by 4 is 0. So I'm getting that y is 0. So when y is 0, this is true. Probably the simplest one to check, right? If I look up here, I've got 3 times 0. That's clearly a 0. And then over here, I have 2 minus 0 plus 2, which is 2 minus 2, which is clearly the number 0. So because both of these end up becoming 0 when y is 0, it's definitely the solution. And then our last exercise here, I have 3 times the quantity of 4x plus 1 equals 159. I'm going to subtract 3 from both sides. So that's going to give me 4 times x plus 1 is equal to 156. And I think the next thing I'm going to do is I'm going to not use the distributive property. I'm actually going to divide both sides by 4. So I get x plus 1 is equal to 156 divided by 4. Or I could say x plus 1 equals 156 over 4. Same thing. So when I do the arithmetic, this becomes x plus 1 equals 39. That's what I get when I take 156 and divide by 4. And finally, if I subtract 1 from each side, x is the number 38. So 38 should make this true. If I look at 3 plus in parentheses, or I'm sorry, 3 plus 4 times the quantity of 38 plus 1, that's 3 plus 4 times 39. 4 times 39, I believe, is 156. 120, 30, 40, yep, it is 156. And 3 plus 156 is 159. So when I plug 38 into this equation, it forces the left-hand side and the right-hand side to become 159. So x equals 39 is our solution. And what were the properties that I used? I guess first of all, I used subtraction property of equality. I subtracted 3 from both sides. Then I used the division property of equality. I divided both sides by 4. The next thing that I did, because this is really a non-step, the next thing I did was basically subtract 1 from both sides, so subtraction property of equality.